just expand upon that. My goal, of course, is to give you guys something useful that you can take away from this. Of course, you know, like I said, the promised thing in the title, a discussion of functional programming in Rust itself. I wanted to highlight it because it's funny. It's actually just one part of the talk, and there's a bunch of other stuff, you know, that ends up kind of coming up and overruling that. I want to also talk about, you know, in context for Rust. I want to present some entry points for different kinds of programming where Rust is popular, for anybody, you know, who wants to do certain kinds of things, whether it's game dev or embedded programming, you know, just kind of to provide some pointers for where you can go to find out more information. There's a couple of things I think that are really exciting about the future of you know, stable Rust, I should say, because there's all kinds of wild stuff in the nightly builds, but much of it never makes it out or will stay in the nightly builds forever, just because of the nature of it. So that's some of the things that are making it into, you know, the stable main branches is going to be really cool. So I'm excited about that. The first, I want to just really quickly kind of talk about Rust in brief. Rust is multi-paradigm, which is to say it accommodates a more object-oriented style where data-bearing structures manage their internal state via methods. You know, the way that we have kind of a concept of structures holding data matched forward to methods, or, you know, doing certain kinds of like inheritance-based polymorphism is through what's called a trait system, which, if you're familiar with Haskell, is basically like Haskell type classes where you specify a trait and then you have to implement that trait. It kind of ends up being like a three-way pivot between the specification of the trait and then implement a concrete implementation of the trait for you know, a data structure, and where you actually will spell out methods, and then, you know, you can have default methods and so on that are already defined. You know, those are features that you're seeing that are leaking back up into, like, you know, .NET Core with the default implementations on interfaces. So that's pretty exciting. As well as within Rust accommodates more functional styles, you know, that focus on things like immutability, declarative patterns, and purity in design. The classic description of the project, of course, is that it pursues the trifecta of safety. I would say in safety in terms of memory access. That's a really important caveat that really needs to be emphasized. Performance, in this case, chasing a C++-like performance profile and benchmarks, which I think the project has been pretty good about doing, and concurrency, which I would point out is subordinate to safety. As anybody who's done any amount of multi-threaded programming in Rust will tell you, the compiler will get on you pretty quick because it is a harsh taskmaster. Rust has a broadly C-like syntax with some conveniences, like the fact that many of the control flow structures, like if-else, are expression style. So you can use them like you would in like OCaml or in an ML language, where you can use ifs basically to, you know, do conditional values, where things that you would do in like C with ternary expressions. So you have, but, you know, just more the idea that, like, you know, like that all blocks naturally become expression based. So you have things like return position becomes important, and, you know, things that, like, you don't really think about if you're programming in a C-like language, but that languages like, even like, you know, Scala, F#, and stuff like that, that kind of, like, you know, even if you're doing a more imperative style, things that fall out pretty naturally. Sorry, just a sec. There are also other nuances of the language. It has an LLK grammar, so some things that fall out of that is that parentheses are optional in like control flow structures, like around ifs. You don't have to use parentheses, but brackets always end up being required for all blocks, except for like single expression closures, or, you know, like inline specified you know, functions. And so, you know, because there's always blocks for control flow structures, and you don't have things like sentinel clauses or accidental fall through, there's no case structures. Another OCaml influence worth noting is the compiler's default allowance of shadowing variables, which is, you know, redeclaring the same variable over and over, even though it has a different backing type as, you know, it gets consumed and used. That's something that, you know, it seems to be like a more functional style, and it becomes pretty useful in Rust when you're dealing with linear types that, you know, you basically consume and excrete new values over and over. Rust is statically typed with a rich type system that's most often compared to Haskell, but it's worth noting that it includes a few features, mostly because of the borrowing and like value moving systems, that really, like, only can you match or surpass when you get into dependently typed systems like Coke or Agda. And so, but that being said, of course, Haskell has, out of the box, like higher kinded types, that are expressible in the language right now. Rust is coming about with a way to have the same level of expression, but they're approaching it from a different angle, I would say. Because, I mean, if you look at HKT, you understand that it requires basically runtime. Like there's a lot of runtime stuff happening under the covers. And so with Rust, you don't necessarily have that. A major goal of Rust has also been to expose what's commonly called a C-like memory model, which is usually shorthand for something much closer to how a processor actually works, although you don't, get access to registers and stuff. This is most important when you compare Rust against more pure functional languages, who by their very design kind of require pervasive uses of things like linked list and hidden heap allocations under the covers and garbage collection to kind of abstract away and give you like a more pure environment to work in. The goal for Rust is to not compromise on any memory access functionality offered by C and C++. And, because Rust also includes a robust foreign function interface for consuming and exposing Rust code to C and C++, like those things being hard constraints, ultimately those are things that kind of chew away at a lot of like the functional conveniences that you see in other more pure languages. In line with above, like the focus on zero, performance and transparent memory access, Rust focuses, and you end up seeing it kind of borne out in a lot of the standard library types, and of course library types produced by vendors, is the focus on zero cost abstractions and a lot of RIAA, like resource acquisition, is initialization style patterns that arise as a result. So, if you're familiar with, particularly in like C++, Rust has got you there, and it's still there. Rust also boasts, I would say, what I think is the most robust developer tool chain out there. And perhaps if there are any dedicated Haskell or, OCaml or Go or Node developers who feel otherwise, then I'm sorry. Reasonable minds can disagree on this, I hope. So don't flame me too hard. Moving on to talking about Rust, the project itself. It started out initially as a project of a gentleman named Graydon Hoare, a Canadian developer who I believe he did undergrad in math and then a master's in CS before moving on to industry work. Most of his work in his CV is around kind of compilers and what he calls industrial C++, so kind of working on like high performance, high availability systems that, because of implementation needs, need to move lower down the stack and away from, virtual runtime environments. So that was kind of his experience. And then he ended up landing at Mozilla, where, a major issue for them is basically their, at that point, 15 years old, give or take, depending on how you track the age of Mozilla going back to, its various incarnations. An old, very mature, very large C++ code base, and them dealing with, basically memory related issues. And, as that being a major source of bugs and vulnerabilities and for them. And so for him, the motivation to make Rust would be summed up, I guess, like so, and this is paraphrasing a 2019 Twitter exchange that he had. He said he saw Rust as, and I quote, like throwing C++ folks, including myself, a life raft with regard to safety. Safety is the thing. The C++, we want to hit the C++ niche, but we want memory safe and including race-free multi-threading, and that's hard. And so kind of working on, that project he started with, if the original Rust compiler was done in OCaml. And while he was working on it at Mozilla, they began sponsoring the project, and they helped put together a team of researchers, particularly a gentleman named Nico Matsakis, who made what I would say are some pretty critical contributions that I'll get into a little bit later. Eventually, with that, with the team together, the core compiler was rewritten and became self-hosting around, before the project was announced in 2010. And then between 2010 and its 1.0 release, they iterated on a lot of features, including adding the borrowing system didn't exist at the time of the first alpha release. And the way that they were basically dealing with memory safety was kind of with like annotations that separated heap allocated from like locally in-thread reference counted things from pure value types. And they eventually iterated towards a system that ended up being more like C and C++, but had, the borrowing system included, which itself is kind of an extension of a Cyclone, if you're familiar with that, which was a C dialect, a kind of experimental research C dialect that had some early versions of what, would become the borrowing, becomes the borrowing system in Rust. So like I said, including the borrowing system, just making changes to the language to hew even closer to a true C++ memory and runtime model. The early version of the language actually had like a checked constraint or contracts feature, like where you could put constraints on functions. That was removed. Like I said, retooling of syntax, references, boxes, which are, Rust basically library type for dealing with heap values, or memory allocated on the heap. And then, of course, the introduction of mutability kind of as a core concept for when you, like at the time of specifying a slot or a variable, specifying mutability and kind of the things that fall out from that. All of that was done before reaching 1.0 in 2015. And since the 1.0 release, changes to Rust have been organized into 3 rolling offerings. There's a nightly version of Rust that's built and released, of course, nightly based on the state, the passing state of the trunk of the Git repository. So if the main trunk is passing, then they'll release. They have a rolling beta release that I believe it is updated every 6 weeks, and things that quote unquote graduate out of the nightly, they go into the beta release. And then they're there and they'll stay there for a while. And then finally, there's a stable release that contains features graduating out of the beta on a rolling, consistent 6-week basis. The latest release is Rust 1.56.1. This is a point release on the 1.56.0 to address a code formatting CVE. It's actually a really interesting vulnerability. And if you go read the 1.56.1 announcement, it points at them. Basically, they introduced with 1.56.0, allowing you to use like arbitrary Unicode for identifiers, which wasn't a thing before. And so when you have arbitrary Unicode and identifiers, there's ways to sneak in like basically empty identifiers that would mess up the code formatting based on whether it was right to left or left to right. And so you could get this situation where somebody could maliciously basically pollute the identifier spaces so that basically code, when you looked at it as a raw file versus when it was actually compiled, it would actually look different in different situations. And so they have they did a release to address that. And then finally, Rust also periodically releases additions that represent basically breaking changes compared to previous editions. So when Rust 1.0 was released, Rust 2015 was the edition that was released at that time. Regardless of the version, all prior editions will be supported in the compiler, and individual crates opt into which edition they support. The latest Rust edition is 2021, which, like I said, or I don't know if I had mentioned it, it actually was debuted at the same time as the most recent Rust release, 1.56, which was at the in late October. As noted before, of course, Rust is an open source project, and it's developed out in the open on GitHub. They developed a lot of really amazing build infrastructure, and I'd say that it's a huge part of their project expenses, just running their build infrastructure, considering the amount of stuff they're doing. And just talking about contributing to Rust, it could be its own discussion. So if that's something you're interested in, or learning more about the project structure and kind of, what all is there and how you can get involved, I just recommend checking out rustlang.org to learn more. Of course, Rust was originally owned as a project within Mozilla, but has since been spun out and is now governed by an independent nonprofit that manages trademarks and copyrights and provides a funding structure for sponsors. I also read after I made this slide, actually, that a new batch of sponsors just joined this month. including ARM and Toyota or others. I don't know. Are there any MISRA C programmers here? Anybody know what I'm talking about? Any good stuff? Any embedded folks tonight? No. Okay. Yeah. So it's interesting that an auto manufacturer is coming on, because what they have right now for the state of the art for auto programming is pretty gnarly. If you're curious, like I said, look up MISRA C, MISRA. And so since before the 1.0 release, the Rust team has been doing most of their feature development out in the open through a public RFC process, where the community members suggest features kind of as in a standardized essay format, and they have a place to kind of discuss and debate about that. And then also, you know, the RFCs themselves kind of become tagged and numbered so that they can be referenced explicitly in subsequent pull requests. The Rust governance structure features a core team that oversees the directions of the project, and then sub-team leadership, leadership of sub-teams, and then cross-cutting concerns. Sub-teams cover everything from the compiler, infrastructure, language features, Crate.io management. Crates.io is the website for kind of the backing package system for Rust. I won't have a lot of time to get into the developer tooling, but you know, it bears mentioning that Rust ships an official supported package repository akin to NPM, but with many features that are more appropriate to the fact that it's shipping native code, and a lot of, you know, like dealing with different platforms and so on. And of course, like I said, dev tooling, community moderation, releases, etc. So for next, I want to dive into talking about the key trade-offs of Rust. But first, let's actually show some code. So what I'm going to do here is I'm going to go and actually just use the Rust tooling. Everybody can see my, that's not too small, is it, my PowerShell window? So I'm going to go ahead.
It's pretty small.
Okay. So what I'm doing here is that a little better?
Yeah.
Okay, what I'm doing here is really quickly just spinning up a new
You chip it by Claude a bigger screen.
Well, that is true. That is true.
So really, I use Cargo, which is Rust's basically package and project management tool to initialize a new project. And so what it did was it spun up this library, and also it made it a valid Git repository. So that's here and it's in place for us. And then I just opened a Visual Studio window. First class Rust tooling is available in VS Code. If you want to do that, I would just install it. Recommend just getting the Rust extension. So what we get here is, of course, like I said, this is a Git repository. So they give us kind of a Git style, you know, git ignore. And then this TOML file is basically the manifest. If you're familiar with, you know, NPM or, you know, applications or package roots, this is equivalent to, you know, the package JSON. And so you can specify a lot of the same stuff, although it has a lot more stuff that is, you know, germane just to Rust. But in the actual source itself, we actually have the library. And so what they gave us here was just this little, actually just a bit of test code. So really quickly, what we have here is this is a basically a compiler directive that says to only compile this code when we're compiling for tests. And so the compiler will know whether it's compiling for a build, debug, production, or, you know, test. And it does basically, you know, that affects the size of the binary. By convention, Rust, they don't have separate libraries or even separate files. Usually the tests are in line as freestanding functions alongside where actual implementation is. That's just kind of by convention. That's the way that, you know, they've done it. So really quick though, I just want to go ahead and make a function that does a thing. And go ahead and then, oh, whoops. Excuse me, and use it. So here, just really quick within this function, we can see, I can do, once again, I can use the Cargo tooling and it'll go ahead and it runs this one out of the box test. So I want to go ahead and just use this, and I want to go and I want to run it. Oh, whoops, I did not save. Whoa, what's this about? It's complaining. It says it can't find this function in scope. What's that about? Well, it turns out that what I need to do in order to make use of this is I actually have to import this thing in. And so in order to get that to work. So that kind of brings us to the first lesson of Rust, which is that Rust really favors explicit over succinctness. That is, the Rust compiler will almost always push you towards explicitly spelling out your expectations. It assumes very little, and most of the stuff where it does assumptions is for convenience around managing references and values. But for almost everything else, the compiler will make you pay if you don't spell it all out. And I'd say, as part of that, Rust already has a reputation, rightly earned, for having a really dense syntax with a lot of gotchas from the compiler. And this is, of course, part of the design of the language. So if you don't like it, this is kind of where it's at. I doubt it's going to get much simpler. Your alternatives are probably Swift or maybe Haskell. I don't know. So have at it. I'm kidding, of course. I know there actually are lots of other platforms, like your guy who gave the presentation a couple months back talking about Elm and his platform he was working on. So there's a lot of people who are kind of tackling, what Rust is doing from different angles. Although I would say that that platform was a lot more loosely typed than Rust. So next, none of the next key trade-offs with Rust, of course, and I've hinted at this a lot, is that performance over convenience. And so Rust by its nature really cares about performance. Its history as a Mozilla project meant that, for them to be able to replace parts of the Mozilla browser, which itself, as I mentioned, is a massive C++ code base, that's what they wanted to do with it. And so what they had to be able to do was, have transparent memory access and give developers tools to reason about how intensive their programs will be, which, almost 95% of the time comes down to really just being able to reason about memory allocations. And if you can get that down and you can tighten that up, that's where, the lion's share of optimizations and code bases come. And this is, of course, because Rust doesn't do much magic under the hood with memory allocation. And so kind of to demonstrate this table that I have here, I've included it from the embedded Rust book, which is actually really cool. If you go out and Google it, Rust Embedded, I believe, Rust Embedded or the Rust Embedded book. They've got an online document for it. And this table outlines the impact of marking your crate. And so that's when I talk about marking the crate, that would be within that cargo toml file, which I mentioned is the manifest, specifying no STD. And so what that means is basically building the crate, your dependency, whether it's an application or a library, without any dependencies on the Rust standard library. And so what you can see here, what you get when you do no STD is you lose heap allocated types. And so things that build on top of heap allocation, so specifically there's some memAlloc, a method within there that does, for doing heap allocations. The things that build upon that in the library, like vectors, which is basically where you would use like a linked list, or just an infinitely expanding list, although the implementation is different from the linked list. So it's not fair to call it that, but you'd use it basically in the same way. Or hash maps, which is like their equivalent of a dictionary type. You basically don't have access to any of that. You can see Stack Overflow protection gets stripped out. There's certain libraries or dependencies where you can specify initialization code, which will actually be ran before the main entry point of the program. That goes away. And then, of course, the standard library, which is, the majority of, the officially supported code is within there, but there's a smaller library called libcore that has basically all stack allocated types and abstractions that is still available. And what you get when you strip away the standard library is a massively smaller binary that is appropriate for using when you're writing firmwares, doing firmware code or kernels or bootloader stuff. So, the fact that that's possible in Rust is kind of a testament to kind of where, they're going, because we take it for granted that languages like C just do that out of the box because they were purpose built for that, because of the era in which they were built and the abstractions that were, at the time of C's debut was considered incredibly high level. But nowadays, what C considers high level is actually really low level for what us as application developers deal with. So to come back and actually approach that and take that problem on to be able to meet it there requires a lot of stuff that, you have to think about and deal with. That isn't obvious at first. You think, oh, this would be easy. I could do, like anything more complicated than a fourth interpreter. Basically, it gets really hard. So the next item, of course, I mentioned, with key trade-offs in Rust is memory safety. Memory safety is really, really important. And so pretty much when anybody's talking about safety in Rust, really they're just talking about memory safety. And so it's pretty important to kind of grasp that. And, there's some things kind of that I'll hint at and talk about in this talk that I gloss over, but I just want to reemphasize. So things like move types, value consumptions, they constitute what's called a linear type, like in type theory, which means basically like a thing that's there or not. And, it specifies that like as part of a type's life cycle, you include the concept of it being consumed and being destroyed. And so with that and how it complements the borrowing lifetime system in Rust, natural patterns arise that kind of allow developers to design systems that I think, include that kind of safety. And then also examples that I show in this talk with closures and Lambda methods, basically, they allied a lot with how Rust distinguishes between pure functions and closures within code. And, the difference between a pure function and a closure is closures capture values out of their enclosing lexical environment and then incorporate that as part of their value for their lifetime. So that has implications for, in a language where you do manual memory management that don't come up in garbage collected languages. If any of you, I don't know if any are there C+ who are modern C++ developers here, you know that when they introduce the Lambda syntax, there's also a pretty heavy syntax for captures and how captures happen. And so Rust also has to account for some of that stuff. But anyway, the important thing is that because of memory safety and because of the borrowing system, there's a subtle and difficult to reason about issues that can arise, particularly when working with higher order functions. And I will get into some of that.
I do have a question about the borrow system. If I remember correctly, there's only, you can have multiple writers and one reader. Is that the situation?
You're talking about for referencing, for mutable versus immutable references?
Yeah.
So it'll be the other way around, and it depends on what's happening. So if there are mutable references held, then you can't take a mutable reference because you might mutate it out from somebody. But when or excuse me, it's the other way around. So you can hold multiple immutable references, but only a single mutator at a time. And then if a mutable reference is held, then new immutable references won't be allowed.
Okay.
So I guess wrapping up on this with the trade-offs, if you imagine a continuum with the lambda calculus on the left-hand side and machine instructions on the right, for me, Rust comes down somewhere in the center right. Like I said, it includes and a lot of stuff in its type system and conveniences that are obviously descended from the ML line of languages. And as I mentioned, besides C++, Graydon Hoare himself is a big OCaml guy. But in the end, again and again, where it has to, Rust always goes on the side of basically coming down more towards C and C++ as it has to do with memory management. And so for that reason, there's a bunch of you kind of end up kicking the box out from underneath a bunch of functional stuff that you'd have otherwise. So next, I'm going to go ahead and do a whirlwind tour of Rust syntax and features. And so I'm going to talk about all these items. I'm just going to kind of blow through a source code file that I have kind of set aside for this to talk about these things. So first we have control flow. And so as you see here, ifs, the blocks are always there, but there's no parens that are necessary. And basically C style if and else. What we have here is basically expression style use of if and else to capture a value out of it. The compiler will look and verify, it does all the type stuff to make sure you don't return, type F out of another one and type T out of the other, so you have to match all that stuff up. You get all that for free, of course, because this is a statically typed language, all of these things, even though you don't specify explicit type. You can get pretty far in Rust without having to specify the type at the point of where you define variables, but occasionally it becomes the thing if there's enough ambiguity in what it is that's being done. Next, we want to talk about closures, of course. So this is the syntax right here for just a basic closure. You can see that has multiple statements. It doesn't emit any return values, and it has no input. So if there was values in here, like this would be, this would become an input value that would need to be provided. But what it does show is it shows capturing out of the environment. And so this is a closure. This isn't a pure function because it doesn't take any inputs. It doesn't return any outputs. So it's kind of a black box what it does. So, I mean, by there kind of, questions whether it could be pure, but it also is capturing this value out of here. And it's doing this by taking a mutable reference to this already stored mutable value. And of course, in terms of stuff that Rust does for free, if that mute went away from after the let keyword, then suddenly this is an immutable value and we can't take a mutable reference to that. So this kind of gives a hint to kind of how Rust deals with mutability at the point of slot definition. So like if you have a structure that has values within it, those values themselves don't have their mutability specified. It's always at the point of the exterior storage of the enclosing type. And so, you can have basically cascading, hierarchies arise out of that. There are some library types that are meant kind of to do or to allow you to have that, kind of by their nature and design, allow basically side effects to leak out of what looks like an immutable type. And that mostly happens with like unsafe code under the covers, and it's kind of in, limited circumstances. But like I said here with this example, you can see this is a closure capturing a value and then doing a mutation on it. It has to, this right here is it dereferencing the value because this is a reference, of course. And then so that it can mutate it, and then coming down here, actually, executing that type or that function that was specified here, this closure, and then being able to look at, its value before and after. Next, I want to talk really briefly about kind of array types. So one of the things that's notable about them is that their length is a part of their value specification. And I guess also speaking really briefly, talking about basic syntax. So let is, of course, familiar with OCaml, it's specifying a type. This is the variable name. If you're specifying the explicit type, it follows after with the colon, like so. And then this, of course, is initialization. Rust is, one of those languages that won't let you initialize empty values. There's no concept of a null value within the core within the safe core language itself. So everything needs to be initialized, and it validates that. Here you can see this is basically different syntax for initialization. Like if you wanted to just, build out an empty 500 element array, you can see how you can do that, or you can specify each individual item, or of course, at runtime, of course, you're going to have different values. They're going to be dynamically constructed. But it's interesting to note that, like I said, that length is a part of array type specification. And so this right here, this is a stack allocated type. Is what that is. And so, of course, we have normal indexing into arrays, and then we have typical, types, or, basically convenience helper functions out of the standard library. You can see that the arrays are stack allocated, so we can basically look at the memory footprint of it and actually see that it's going to be size of int32 times 500 or whatever. And then we get into kind of a basic example of borrowing. So I mentioned this before up here with this, this constitutes a borrow, taking a reference to this thing. And so borrowing refers to the system of the compiler. It's its referencing system, but it's accounting for all references taken, and it's making sure that any reference taken doesn't violate mutability constraints based upon the type. It makes sure that any references taken, that the value where the reference is taken isn't released while a reference is held. You know, a bunch of things that ensure kind of the soundness and memory safety guarantees of the language. So what this ends up being is a slice, which, you know, a reference referring to, and so this is a special type annotation. So it looks like the array, but it doesn't have the length specification as part of the type signature, and it just has this to specify. So this is just, it just lets you know that this is some amount of elements of type I32, and then it's able to work upon them here. Another thing that's interesting, of course, is that because array types are static at the time of definition, you can see that this particular definition of this type XS, this is invalid because, you know, it only has 5 elements. So with a zero-based array index, this is beyond. So that's kind of just, you know, showing what it is there. Next, I want to talk about enums. It's funny, kind of enums popped up before talking about structs, and so you can kind of construct more more complex types out of combinations of the two. But enums, of course, are, you know, algebraic data types, if you're familiar with them from you know, F#, OCaml, and Haskell. You know, they're there. These are kind of basic enums, but of course enums can have like arbitrary density or complexity. This is an example. So I mean, really quick, you can see, you know, kind of the ways that you can do pattern matching that arises off of enums. That's kind of really the you know, exhaustive pattern matching is probably one of the main things, and the destructuring that you're allowed to do out of that. And you know, you want, and of course enums are also, like, in memory, they're similar to tagged unions in C. So basically what they carry is, you know, a region that's the size of the largest enum variant, and then a tag, and then it knows basically to swap out the contents based on what the current variant is. But in memory, you know, they look basically like C unions with an additional tag. This is an example of a slightly more complex list that pretty much mimics like a const style, you know, linked list, where the enum can have 2 possible values. It's either this contents of itself, which is its current value, and then a box, which is, you know, heap allocated value pointing to the next item in the linked list. And that thing itself can either be another one of these, or it can be a nil value specifying the end of the list. So that's kind of an example, you know, how, you know, ways that enums can be used. But I mean, really, like, enums arise in systems, like you'll see a lot of, like, I don't know, error types that are manifested as enums, so that each variant can carry custom information. You know, if you have a, you know, TCP packet processor, the variants might be different kinds of, you know, packet protocols built on top of TCP. You know, the sky's the limit. And so, of course, if you guys come from a functional programming background, particularly in Haskell or F# or OCaml, then that is nothing new. Moving on, of course, we have structs as well, which are pretty much more C-style memory layout data structures. So those are really straightforward. You can also have what are called unit structs, which basically function as like atoms. They have no value except for themselves, or like an enum with only a single variant is another way to think about them. And then you can also have tuple values, where you don't care about the names or identifiers of them. You just care about them as basically, you know, ordered combinations of values, which you'll destructure at some point in the future. I haven't shown it really here, but Rust includes robust destructuring syntax like you would do in Haskell or OCaml or F#. So, you know, taking apart values, and then all of the destructuring capability exists in the pattern matching system itself. And as time goes on, Rust seems to get, they're actually putting a lot of work into kind of making the pattern matching system itself more robust and more convenient to use. But that stuff is totally, like, I don't have time to cover that, unfortunately. I'm already over time. And moving on to the next item, I wanted to talk about kind of give a practical example of the borrowing system itself. So this function itself kind of constitutes kind of a discussion of kind of gotchas with the borrowing system. So when we start out with this, we're creating two values. One of them is a boxed value that just contains an integer. If you're, I guess, F# and OCaml style kind of annotations, you can also do stuff like, excuse me, like that, and to have instead of commas for breaking up large numeric values. And then, but Rust has for its type literals basically, I32, U32, int64, etc. And those things are, they come out naturally in the expressions of the types. There's no, there's no platform dependent, like whatever the platform says a number is, like that thing, how there is in C, where you can have 16 or 32 or 64-bit integers, depending on the platform standard. So here we lay out these two values. One is boxed and one's placed on the stack. And then all these methods do is basically just exist to kind of demonstrate what they would do with these things. So with the function signature of this borrowed I32 value, it is a reference that's been taken to this thing. And contrast that against this eat box I32, what it does is it takes this by value. And so it says this function takes ownership of the box. Because of the way that this is annotated, it's taking the box by value. So whenever this is called, that value goes away. So here we have some examples of how we can see, we can borrow and work on these values, maybe use them for subordinate, calculations or whatever. And, these methods save memory because they just do pointer access to this thing that lives on a higher frame of the stack, instead of having to pass it by value and copy it into their own stack or something like that. So, there's that convenience there. And then within this nested block, we see doing some things like here, that boxed value, which, it represents a heap allocated value, but it exists as a value. They have a reference taken to it. And so that reference can be used within here. But if we did something like this, like uncommenting this method right here and ate it, then what happens is this boxed value, it would be destroyed at this point, or it'd be consumed and not emitted out. And so this breaks right now because that subsequent call to try and borrow it, but this becomes legal once that's commented out. Also, subsequently, because of that, this call now is no longer valid because this boxed value is already eaten up here. So these are all things that are basically happening just because of oops, I commented the wrong line. These are things that are happening because of Rust's borrow checking system, and pretty much all it's doing is validating that what you're doing with values and their variables and how you're referring to them, that all of it basically ties out within the current context. And it's able to do this across functions and across function call boundaries, and then basically to the entire boundaries within a crate, and then doing whole program analysis when it actually links a program together to enforce these constraints. Next, I want to talk briefly about traits. Like I said, this is how you this is how you do like inheritance polymorphism, which you would do with classes in C# or with type classes, which Rust traits are almost exactly like. You're able to basically specify the trait and say, here's the behavior I want implemented. You can provide default implementations. These can also be overridden in implementers. The Rust provides the ability to do like a bare implementation just against a structure itself. So these will be basically these will be methods that will be available when you're interacting with the concrete type itself. If this was cast or type into, cast or boxed into just the trait, then there would be basically those things aren't available. So this is, kind of, encapsulation and hiding functionality. And then finally, we have the implementation of the animal trait for a sheep, basically with the defining of methods that do things on the sheep itself. All of this is kind of, really noisy, but just to kind of demonstrate, like I said, there's kind of this three-way pivot. And so it's interesting where, you either have to own a concrete type or the trait itself in order to do anything useful. So if you have like a library type and there's a trait that you wanted to have it implement, like, you know, the challenge to be able to do that, it kind of becomes tricky based on where things are. And so it's, you know, you're expected to be able to have like, you know, interior ownership of either a trait or a concrete type. And then finally, oh no, excuse me, that was just the thing for that. Okay, ready to move on. So that was kind of, like I said, just kind of a quick overview of the syntax. Was there anything here that was like really puzzling or weird to anybody? I know I'm covering a whole bunch of stuff and I'm moving really fast. Is there any questions before I move on?
Sure. Just a real quick question. Can the implementations, I mean, do they have to, I guess, you said you had to own either the trait or the class. So can
Yeah.
the implementations occur in like other files? So if I import like type animal from a cargo, like from a you know, a package, and then I can implement
Yeah.
that for sheep. Or I could import sheep and then implement animal for in my
no, it's at the crate boundary, and so you can't pull in someone else's, you know, crate, and then, you know, because it's like if there's like a library that you want that has a trait, and then some other, you know, library that you want to implement that trait for, like you don't own either of those things, so you have to ask one or the other, basically, you know, to, yeah.
Okay, cool, thanks.
All right, finally, so we can talk about functional Rust now. Now we're here to the meat of it last. So in order to talk about functional Rust, we have to kind of set some boundaries around what exactly is functional. So for this, I'm going to kind of give the hand wavy answer of saying that there are certain principles which make code more functional. Some languages make this easier or harder to adhere to, and generally speaking, languages that make it easier to adhere to functional principles are considered functional languages. And even if they do that, though, they often they make it harder to violate these functional principles. But however, you know, almost always there's some way for you to do it, to break, you know, functional principle encapsulation or whatever you want to call it, if the situation demands it. But in general, we have these things that we say, if a language or a system is more like this or it supports this, then we consider it more functional. And so those things are, I guess, really briefly, I would say mutability, you know, having to do with kind of how you treat values and how they're changed and how, you know, they are applied within functions. I would say recursion is an important part of it. And then also, of course, I would say higher order functions and kind of function pipelining become, you know, are things that are kind of like, you know, they really play out a lot in functional languages and kind of become core things. So with that in mind, I would say talking about mutability, I mean, just looking at, excuse me, some of the previous examples, like where we talked about with the borrowing system, I think that it's pretty self-evident that, you know, Rust has strong controls around mutability. Of course, it allows you to break those, you know, rules or to make things mutable. But out of the box and the behavior, you know, it's perfectly possible to write pure functions and pure programs in Rust, you know, because of just, you know, the basic building blocks are there. Next, when I talk about recursion, I'll just say really quick, Rust doesn't have any tail call optimization. So if you want to do a system where you're gonna where you would have something like some infinite recursion, you can and will very much get stack overflows like this example here shows. You absolutely, you know, will blow up in this case because this will just recurse until it runs out of stack. You know, and you don't really need to implement your own trampoline, which is the way, you know, that like you kind of do a recursion like functionality in systems that don't have it. Because we have Rust has what are called iterators, which is pretty much a trait and a language support feature for doing iteration over you know, values that are amenable to be iterated over. And the way that it's implemented, it allows you to kind of have like dynamic infinite objects or objects that block the next time you try to go to an iteration or something like that. So that you'd end up doing a lot of the things that you would when you use recursion as a control flow mechanism in functional programming. And then of course, talking again about higher order functions, you know, this is kind of the idea, right, that where you pretty much just compose pipelines of functions working on values and mutating them until eventually you get the thing you want. And so this is kind of an idiomatic example of how, you would take, create a value from 0 to 100 and then, double those and then sum them back together. And so you can kind of see, I had just kind of the Haskell golf parlor trick version of this to put it alongside what you would do in Rust to show that while it is a bit more verbose, it's pretty close. And that being said, I'll say that a lot of the cool stuff that you're used to if you're doing a lot of hardcore like statically typed functional programming, and also I'll say this as a Haskell baby, I'm pretty new to Haskell. I mostly come to it through Elm, and I've wanted to do more, but I'm still on that journey. But a lot of stuff that you would do idiomatically in those languages, like currying, doesn't exist. Like point free style, like pipelining, doesn't exist in Rust. So you do kind of, the same tools aren't there kind of to use higher order functions in like really, I guess like intention revealing and in more declarative ways, because Rust makes you do a lot more bookkeeping. And also the thing I mentioned earlier about memory safety and closures, it's really easy when you're working with closures. So these are all just pure functions. These are reified as function pointers at runtime. They don't have any additional state with them because they don't capture anything out of enclosing context. But as soon as you start having things where like it really makes sense to do that and you start capturing stuff, it becomes really hard to actually use a closure. And so you have to kind of fall back to a couple of things like generic traits and methods that consume them. And it kind of, it gets complicated and it limits utility. And this kind of plays into the memory safety. And especially once you get into like multi-threaded programming, because almost any like in C or C, like ultimately in any language, or any asynchronous backend, when you want to spawn a new thread or some kind of background process, you say run this function pointer, basically is what it always comes down to. And so in Rust, at the point where you have to pass that function pointer, if it's not, just a bare function pointer, then things get complicated. So that's where, like if you're trying to capture anything, useful, that's a situation that rises in Rust where, I think developers end up having their hands tied. And then last, like I said, kind of, because recursion isn't there, what we see instead is iterators. And so this right here is just the declaration of a vector. So this is a special shorthand form for declaring a vector, which is Rust's name for like a linked list or a dynamically expanding list, was what they would be in other languages. And so then this is kind of the natural way to iterate over them. But what's happening here actually is this is all desugared syntax for basically doing this. And so if you kind of this stuff right here, this is kind of what it actually looks like at runtime. And so what we're doing here with this vector is we're turning it into an iterator, and we're making it mutable, of course, in the process. And then you have to iterate over it in that process. And so this while is pretty much simulating that process. This next returns an option, and so this let sum is actually is a sort of it's a sort of conditional expression that's saying while the result of this next call is a sum value, because this actually returns an option, which is a sum or a none of t. And so this says while this iterator.next call is returning a sum, and this is the value that's bound for use within this block, keep running this while loop. But once this next reaches the end, it'll return a none, and then this loop would break out. So that's kind of like what this boils down to. And so just looking at that and seeing that, you can kind of see that, taking this syntax and kind of boiling it down to just this is a win. And you can also see that within this natural form, a lot of opportunities to do kind of neat, tricky stuff arise where, the iterator is actually like something that's blocking on external input or, incoming packets in a server or stuff like that. Like there's a lot of, stuff, and these are the same places where you would see like lazy evaluation used in Haskell. All right, so that was functional Rust. All right, so with that out of the way, I wanted to talk a bit about kind of like how you would how people are using Rust in different contexts. So Rust is really, I mean, popular, and I think a lot of people come to it in the context of like backend services that are doing a lot of like data work, low-level IO, or lots of like you know, like DSP type stuff. And these are things that I think a lot of people before now were doing in Node.js, but kind of they hit the limits performance-wise, particularly around like DSP work. That, you know, you see where naturally, if they wanted to go away from, you know, a high level async IO engine like Node, they would have to move. Their next place to go would basically be to C. You know, so now like Rust is becoming more popular in that space. Of course, there's a lot of like, if you got anybody here is into like blockchain technology, Rust is, you know, a lot of the newer, like I'd say like post Ethereum or the quote the Ethereum killer blockchains are coming out. A lot of them like a Solana are having, you know, Rust support as kind of a first class thing. So that's pretty exciting. But there's other places where it's more rough, like some of the tooling, especially for like using Rust as web services, are kind of like more like, you know, application level web services. The tooling is there, but it's rough. So like if you want to use Rust to stand up a RESTful API with JOT authentication, you'll have a lot of stuff that you're going to have to, you know, stumble over, especially once you come into dealing with, you know, integrating with your actual, you know, security or your actual authentication provider, whatever that is. You know, like in a robust modern infrastructure, you're not, you know, the way that we do authentication, a lot of that tooling is still not great in my opinion. And for raw web application work, I mean, Rust itself doesn't have a lot to offer over something like Nginx serving up, you know, like an Angular application. So, you know, it's not a big win there in that space, in my opinion, but some people insist on using it that way. But I think that hopefully once the tooling gets better, particularly around web services, I hope that, you know, Rust will become a good option, especially because of how expressive the type system is. Rust is, on the other hand, seeing a lot of uptake in developer tooling, especially in the web application infrastructure space. If anybody is, you know, really into web application development, Next.js has rewritten pretty much their tooling stack on top of Rust command line tools. Rome, which is the successor to the Babel transpiler, if you're familiar with that, you know, it's kind of one of the first TypeScript transpilers, or excuse me, like ES 2015 transpilers that was out there, you know, that was providing ways to kind of, you know, write more modern versions of JavaScript and then spit them out in, you know, more browser consumable forms. So Rome, the successor to Babel, written by the same author, he is using Rust for that. And there's a lot of others, Deno, SWC, and Parcel, a lot of like, I believe Google, not Google, but Cloudflare and Amazon both have quick parsers, when you know, like HTTP 3.0 parsers written in Rust. So if you want to learn more about that, there's a really good, pretty recent blog post on the topic called Rust is the Future of JavaScript Infrastructure that you can look at to learn more. Of course, Rust has a lot of interest and buzz and also hate, I would say, in the game dev community. There really aren't any like big AAA games that have shipped written in Rust, but it definitely has a lot of interest and there's some great tooling that's there. I like to play around with engines, and there's tons of engines and stuff like that to play with in Rust. If you want to check out one in that, you could look at the Bevy engine, the BEVY. It's a really interesting kind of evented architecture for Rust game, or, you know, like data oriented, like an ECS system. Of course, embedded programming is a popular thing. I talked about that earlier with the no STD annotation and kind of the applications that you can get, what the impact of that is. And of course, while Rust is a challenge and more space constrained, like 8-bit processors, you know, where it's hard to even use C, and you probably have Forth or just straight up machine code. Rust is finding uptake on, you know, platforms that have more headroom. All the tooling and design is there to embed Rust in a way that just isn't possible in most other languages, like I talked about, because they're really grasping with the consequences of trying to have a really C memory compatible language. And dovetailing with the above, of course, the Linux kernel itself is starting to make space, and recently they've done some things to make it possible to basically write drivers and Linux kernel modules in Rust. Chances are there won't ever be Rust itself in the Linux kernel tree because they're, GPL 3 people and Rust is an MIT code base. But I mean, the Rust code itself or whatever, my understanding is that they're just not super enthused about the idea of starting to take on Rust, but vendors will be able to start writing kernel modules and shipping them with their products, or individual companies that, if you're a company that's a big enough deal to have your own, custom kernel modules, think Facebook, Google, etc., they have the tools to be able to use this. Really quickly, talking about the future of Rust, some really cool things that are coming down the pike. So this is stabilization of a feature called GATs, which is generic associated types. And so this is an exciting addition that extends associated types, which is it's a feature that I didn't even talk about in this talk. That goes to show I didn't even really talk about like real type polymorphism that is available in Rust. But associated types are a way to kind of specify like a type slot on a trait separate from like a generic constraint itself. And it just means that the implementers have to specify that type, and then they can reference that type within, their implementation. And so this is an extension to associated types that will allow you to have additional generic annotations on top of that, which kind of gets us pretty close to the idea of types that are abstracted over, that are type, a thing that can deal with a type that is an abstraction over other abstractions itself. So kind of, like a way to chip at higher kinded types within Rust, and then combining that with with a feature that's called const generics, which refers specifically to allow the embedding of const information within a type as a dynamic parameter. And so, and really quickly kind of to demonstrate what that is, like in the example over here where I was talking about the use of arrays. So this is a feature, or basically a part of the type itself. And so that comes out as like, item of T with, a length of K. And so there are T items and they have a length of K. And so within these right here, within arrays, the type is a part of their type definition, but you can't specify a generic type or like set a generic constraint where you can say you have a type of T and that, the length component itself is a generic thing that can be deferred until further on. And so this isn't really the greatest explanation for it, but the idea is that they're making it so that you can have, generic, you can make things that would be size fixed at compile time, like into generic constraints. So you can have like basically a type that represents like a fixed length of something. And so that it'll be pretty interesting for like what's possible in the future. And I think these two things put together are going to kind of be what gets the community towards, being able to have the expressiveness that a lot of folks are looking for with higher kind of types within Rust. So it's pretty exciting. And this stuff is kind of coming down the pike. Hopefully like in the next year, we'll see it on the main branches.
Is there a concept of like generic constraints on those where
Yeah.
You can say it's an implementation of this?
Yeah,
of this
you can say T. Yeah, I don't think I have an example, but yes, they're generic constraints as robust as, I don't know.
So with GAT, could you, for example, say this function operates on an X of T where X is a applicative?
Yeah. So with GAT itself, this is going to manifest the annotation for associated types. It appears within traits themselves. So what it'll allow you to do is write traits that abstract over a type that itself abstracts over an additional type. And you can place, well, and so additionally, so the kind of the thing as well, and something that I completely didn't cover, because like I said, there's just the space is too large in the time that we have. You can also place generic constraints around lifetimes. So you can set constraints and you can carry lifetimes as generic parameters themselves. If you ever see like a lowercase letter preceded by a dash within a generic definition, that's basically a lifetime constraint. And so it's about being able to put lifetimes and within a thing. And so you can specify a trait that is like a T that has a lifetime associated with it that's pegged to some outside type, because that's mostly where like how like within the borrowing system, that's kind of where lifetimes appear within type annotations, is so you can say the type that I'm creating, it's going to contain this other thing, and I'm going to guarantee that my type lives at least as long as this thing does. And you're giving the compiler that information. And so that's a lot of like what it's going to be used for. But I mean, yeah, you wouldn't write a function that way. You basically would write a trait that would have that GAT specification, and then it's going to have methods specified on it that do those things, and then a concrete type comes along and implements that and kind of fills the rest out, although it might still be generic for its T, right? So because that's the higher kindedness of it.
Awesome.
Until it's actually applied at runtime, until it's applied by a consumer, who actually fills out the inner type. Yeah, I guess so that gets into questions. So this is the end. If I had any recommendations, it would be to check out the rustlang.org website. It's incredibly robust and a great gateway. If you want to actually interact with the community, the first place I would recommend going, and maybe this is a generational thing, I don't know, but I would recommend going to the Discord. They have a huge community there. There's it's like a mass, like an IRC network level, large in terms of how many people are there and active. And a lot of the core team are there, and I don't know if actual development work happens there. I believe that the Rust organization itself maintains a separate chat system off of Discord. I forget the name, but there's a lot of stuff there, and that's a great entryway. There's a Reddit community that's really active. If you spend any time on Stack Overflow, there's a lot of Rust activity there, a very popular language on Stack Overflow. So there's a lot of opportunities, of course, to interact and get involved with the community.
I recall there's also Slack that's fairly active.
Oh, really? Yeah, see.
I was going to ask a quick question. So one of the things I really like the trait system in Rust, but I also was intrigued by the macro system. And like it seems like there's a lot of macros that help with quality of life in coding, like the vec macro and the print macro. Is it like, are there a lot of people writing macros these days, or do people sort of just use the handful of macros that exist?
No, there's a lot of, so Diesel, which is a ORM library, makes pervasive use of macros kind of for specifying like ORM models. And then basically, based on like how you specify within the macro, it spits out all the trait implementations and the actual, underlying structures. And then, by convention how to utilize it. Serde, which is kind of the major de facto serialization framework, makes use of macros. And so macros in Rust is kind of a tricky thing because there's multiple things that are called macros. Like there's things that look like attribute annotations that are actually macros. And then there's actual like inline code macros, like where you're basically doing like hygienic code substitution. So
yeah, the exclamation point.
Yeah, exactly. Yeah.
So that's kind of what I was thinking about. And I think like the hygienic code substitution, it actually gets you a long way to
DSLs.
Implementing higher kindred types as well. Like just you can do a lot of sort of interesting parameters and functions on especially like with the vec macro, right? You don't have to specify the length of the array to create to vec in your code. It seemed like something that was really kind of a neat feature, but
I don't know if the vec macro
on your own.
What's that?
Also challenging to write on your own.
Yeah, no, it's easier than machine code, I'll say that.
Oh yeah. Well, the macros, not Rust. Rust is nice. I guess that was it. I was just kind of curious what the status was on macros these days.
they're available. Hygienic macros are in the main language. You can, they're in stable Rust.
So I'm a little disappointed Paul McWhorter didn't show up today. He's mostly does C and C++ development for like video streaming type
Oh yeah,
embedded
DSP.
applications. So yeah, I was really hoping he'd show up just for the questions.
Yeah, that's a sweet spot that Rust is there for. And I mean, it's, I think the proof is in the pudding with, the folks that are using it. I think that if you follow or if you saw what Mozilla was doing with, their kind of experimental browser project, they're doing some really interesting stuff and kind of, just be experimenting with different layout engines because, I mean, HTML display is a hard problem, it turns out. And companies that maintain browsers put a lot of effort into making them fast. So it's a major, kind of desktop optimization problem.
Yeah, so I found myself thinking through your whole presentation about the Talking Head song, Once in a Lifetime. You may find yourself.
Right.
It's like, I don't see Rust as something I would do like in my normal day-to-day stuff. But if I found myself like doing an embedded IoT sort of thing, or, there's, it has these like use cases that are beyond things that I would use my normal languages, which is like F# or C# or whatever, right?
Yeah.
Like, there are clearly things where this would be interesting, and it has the things that I find necessary. Like, I want discriminated unions. I want record types. I want to be able to do things in a reasonable fashion. Like, I'm not really crazy about the semicolons and brackets sort of thing, but, I can deal with that.
Yeah. Yeah, I mean, I guess the goal of the Rust compiler is to not have you go, where is my beautiful wife? This isn't my beautiful house. So nobody's going to come out there and free it from under you, So that's the goal. So that is how it is. Rust is like a Talking Head song for sure. I just watched that video the other day too.
I kind of want to just stop the recording now. That was perfect. So I want to ask a question that is probably totally unfair about sort of like the longevity, stability, and future of Rust. And the idea that I have here is, so the SQLite and Tickle conference was today. And Richard Hipp, the creator of SQLite, gave a keynote basically on the state of SQLite. And one of the things that he was talking about is that one, there's a sort of interest, not just from people, but also from apparently companies in like, would you rewrite SQLite in Rust? And he's like, I don't know about that. But he also has this sense that like within the next 10, 20 years, contracts are going to be like, your software has to be memory safe. It just has to be. And that through contracts, C is just not going to be acceptable anymore. And so he was sort of putting it out there to the conference of like, what do you think about this? And what do you like? Rust is the obvious choice right now, today, of like trying to occupy this C area, but being memory safe. And you got a bunch of SQLite and Tickle people, and they're like, well, it hasn't been around for 30 years, so we don't know.
Yeah,
but,
it's worth mentioning that like I believe SQLite is written in ANSI C and is very portable. So
Yeah.
like there's a certain perspective and also like a major historical inertia to that code base. Also, it's like, isn't it like the zlib license? Like it has like a, I know it doesn't have like a typical open source license. That's
He talked about that. No, it wasn't. He didn't talk about it. It was another presentation. It apparently has a blessing license, which is use this for whatever you wish with our blessing. Like, but yeah, it's anyone can use it for basically anything.
You know, there's like maybe 10 or 20 people I would trust with C, and he's one of them, right? And I think the point about like, yeah, at some point C is not going to be acceptable. Like, we're going to have to do the stuff that we did in C in some other language. Because I don't trust very many people in C.
I mean, most shops that are dealing, they're already beyond that though, and they're on to like C++ with like static analysis suites, like a lot of places that are, doing industrial C++. And also, I mean, there's no C++ defenders here, so we can kick them while they're down. But the C language itself has come a long ways in terms of
we're still being recorded. If you want me to stop the recording, then we can.
No, I mean, I would say the C language itself, and I think that, they really are trying to iterate on it to make it more durable. But I mean, that might just be about the longevity of existing code bases. But if you ask a lot of really experienced C++ people, they're like big mad about Rust because a lot of it is, the way that the compiler, ties their hands and kind of discourages certain approaches. So I think that it'll be a while, and that, a certain generation will just have to move on, but that a new generation who would normally turn to C, and this is already happening. I mean, AWS, they're, in the process basically of, standing up, like you can see it with Firecracker, if you're familiar with that, kind of like, an alternative, like thinner, leaner, virtualization infrastructure running on something less than a full operating system, but still a fully virtualized machine. And, when they're starting for those, basically new architectures from the ground up, the language that, organizations are turning to again and again and again for high throughput, critical, use stuff is always going to be, it seems to be Rust. That's why, and I mentioned it back on the previous slide, when, during the pandemic, Mozilla laid off a quarter of their workforce, and including most of the Rust team. And at that time, they went and they formed a foundation, and the, founding members, who was it? It was Amazon, it was Google, it was Microsoft, and since then, a whole bunch of other companies have joined because, I mean, the value proposition is out there. And, right now that value proposition is basically like large distributed consensus systems, things that are, way past C10K, stuff like that, I mean, so there's a niche for it.
So I was going to just jump in because you brought up something. I actually work with a couple of C++ developers in sort of the CAD side of things of my company. And man, I would love it if they could use Rust. Do you know if Rust is trying to move into like the sort of the CAD market, or sort of the linear algebra processing kind of visual?
I mean, the math libraries are all there in terms of like, there's nothing like, I forget the name of the one big Fortran library. There's nothing that good. But that being said, Rust can directly consume those because Rust has a clean CFFI. So, you can consume all of those big C math libraries if you need to. But also
everyone does.
Yeah.
Python and C and everything.
Yeah.
Don't
There's
try to fight the Fortran people though.
Yeah.
Really quick, I was going to say though, Chris, is that if what you're doing is building, if you have to, in order to extend for your CAD practice, to extend it, if you have to ship C++ libraries basically, or, C++ bins, then what there is a library and project within Rust, within the Rust community called CXX, all caps. And what CXX is, because what Rust provides is the C ABI and C FFI. And so they have a library, there's an official or not an official, but a pretty blessed library that does the C++ side, because like C++ itself doesn't have a stable ABI at the platform level. So it's all down to individual implementations, and so they do most of the work for that. So I believe that if it is if you wanted to say, hey, if you guys wanted to use Rust to ship these kinds of libraries, to put a shim around it so it could be invoked and consumed by a C++ program, I think that the path is there. But of course, most of your hurdles to that are going to be bureaucratic and institutional.
Yeah, and personnel. I mean, they know C++. They're not gonna. But I'd feel so much better if they could use Rust. That's me.
Yeah, it's okay, David.
I do love the language. I think it's a great language. So
yeah,
thumbs up.
So you touched a little bit on Rust in the JavaScript space as far as the backend stuff. Do you see a future in the front end, like the WSL?
Yes. Yes, I forgot to mention, I actually had a note, but I blew past it to talk about Rust and WASM. So, there is really pretty good tooling. Both LLVM has a WASM target, and then also Rust has an experimental backend called CraneLift that was actually written as an extension to TraceMonkey, which is kind of like Mozilla's most recent iteration of their JavaScript engine, what's called ScriptMonkey. And so CraneLift is kind of meant to be like a modular extension to that, which they're using to do all of their WASM interpretation. And so incidentally, what they also have is in the process of building a thing that can do like live JIT of that is you basically get a machine code interpreter in WASM format. So you can basically run Rust C and then have it spit out WASM, and that's there. And there's there's pretty good shims and tools there, like people are able to do like 3D games in various platforms and then ship them on the client and stuff like that. And that's another really strong space for it, of course, because that's what WASM is making possible is basically to have really tight compilers without GC to spit out interpreted code that can just run, and so it'll definitely have a space there for high performance front end applications.
And backend as well. I was recently listening to an interview with Martin Kleppmann, the guy who's writing the auto merge, and one of the things they're talking about doing is rewriting auto merge in Rust. So because it's got that WASM backend, and that makes